5 top ICE on why we can get to ASI faster through ANDSI artificial narrow domain superintelligence than through AGI. The conventional wisdom holds that to get to ASI we must first solve AGI. There's a strong argument to be made that achieving ANDSI artificial narrow domain superintelligence specifically designed to solve ASI will get us there faster. Rather than relying on my personal reasoning, I've asked 5 of our top ICE to present this case. The prompt I used is, in 3 paragraphs present the case for ASI being reached more quickly through ANDSI artificial narrow domain superintelligence specifically designed to achieve ASI than through AGI. Here are the responses. Gemini 3.1. The pursuit of ASI through ANDSI artificial narrow domain superintelligence centers on the strategic bypass of human equivalence as a necessary milestone. Traditional AGI development aims to replicate the full spectrum of human cognitive abilities, including social nuances, emotional intelligence, and general-purpose reasoning. However, proponents of the ANDSI path argue that perfecting these human-centric traits is a massive, time-consuming detour. By narrowing the focus to a superintelligent researcher, a system specifically engineered for recursive self-improvement, hardware optimization, and advanced mathematics, we could theoretically ignite an intelligence explosion without ever building a machine that can write poetry or navigate social politics. The technical efficiency of the ANDSI approach lies in its specialized resource allocation. Developing a generalist intelligence requires solving the brittle nature of AI across thousands of disparate domains simultaneously. In contrast, an ANDSI specialized in AI R&D can operate with superhuman proficiency in the very fields required to accelerate its own evolution. Such a system would be a master of its own architecture, capable of discovering more efficient neural structures and cooling techniques that human engineers might overlook. By focusing solely on the intelligence of intelligence, this narrow superintelligence could collapse the timeline to ASI by automating the most difficult parts of the development cycle. Ultimately, the ANDSI route suggests that ASI is not a destination at the end of a long AGI road, but rather a specialized peak that can be climbed directly. While an AGI might take years to learn the breadth of human experience, a narrow domain superintelligence could potentially reach a point of takeoff within weeks of its creation by ruthlessly optimizing its specific task. This specialized path treats intelligence as a functional tool for problem-solving rather than a mirror of the human mind, allowing for a much faster, albeit more alien, transition to a superintelligent state. GPT 5.2. The ANDSI pathway argues that recursively self-improving systems do not need broad, human-level generality to trigger an intelligence explosion. They need extreme competence in a tightly scoped set of meta-capabilities, formal reasoning, automated theorem proving, experiment design, code synthesis, and hardware-aware optimization. A system engineered to be superintelligent within these domains can directly accelerate the very substrates of AI progress: algorithms, architectures, compilers, and chip layouts, yielding rapid capability gains without first solving the full stack of common-sense reasoning, social cognition, and multimodal grounding required for AGI. By concentrating model capacity, data curation, and evaluation on these leverage points, ANDSI minimizes dilution of learning signal and reduces the combinatorial burden that slows generalist systems. A second pillar is tractability and iteration speed. Narrow domain systems admit precise objectives, dense feedback, and verifiable metrics, e.g., proof correctness, benchmarked speedups, silicon performance per watt, enabling tight optimization loops and reliable automated evaluation. This supports aggressive self-play and self-improvement cycles analogous to but more general than systems like AlphaGo, extending into codebases and research pipelines where correctness can be mechanically checked. In contrast, AGI development must reconcile heterogeneous tasks with sparse, ambiguous rewards and broader safety constraints, which slows iteration and complicates validation. Faster, cleaner feedback in ANDSI makes recursive improvement more feasible and less bottlenecked by human oversight. Finally, ANDSI aligns development resources with the highest marginal returns, improving the tools that improve AI. A domain superintelligent system focused on AI R&D can autonomously search model spaces, discover training curricula, design novel optimization algorithms, and co-design hardware, creating a compounding loop that approaches ASI through successive capability amplification. This tooling-first strategy can outpace AGI because it sidesteps the need to achieve robust general agency before harvesting exponential gains. Instead, it bootstraps from superhuman competence in the domains that most directly govern intelligence growth, allowing ASI to emerge as an engineered consequence of sustained, domain-focused recursive improvement. Sonnet 4.6. The most compelling argument for ANDSI as a faster path to ASI begins with the problem of scope. AGI, by definition, requires building a system that matches or exceeds human-level competence across all cognitive domains simultaneously: language, reasoning, perception, motor control, social intelligence, creativity, and more. This is an extraordinarily broad target, and progress in one domain does not guarantee transfer to others. ANDSI, by contrast, concentrates every resource, compute, data, architectural innovation, and research talent, on the singular goal of recursive self-improvement and intelligence amplification within one tightly scoped domain: the problem of making AI smarter. History suggests that focused, well-scoped engineering challenges are solved faster than sprawling, poorly bounded ones. An ANDSI optimized purely for AI research, automated theorem-proving, and system architecture design could iterate and improve on its own design at speeds no human team could match, potentially crossing into superintelligence before AGI researchers have even resolved foundational debates about general cognition. The second argument concerns alignment tractability and safety-compatible speed. One of the reasons AGI development is slow is that researchers are rightly cautious. A general agent with broad capability is broadly dangerous if misaligned. ANDSI offers a narrower attack surface. A system whose capabilities are deliberately constrained to the domain of AI development itself can be more rigorously sandboxed, monitored, and red-teamed, because the space of actions it can take is far more predictable. This means researchers may be able to move faster with ANDSI than with AGI, precisely because the safety overhead is lower and the failure modes are more legible. Faster iteration cycles, more aggressive deployment of experimental architectures, and tighter feedback loops between capability gains and safety evaluation all become feasible when you're not managing a system that could, say, spontaneously develop persuasion or physical manipulation capabilities. Finally, there is the argument from bootstrapping leverage. An ANDSI purpose-built to accelerate AI research would compound its gains in a way that AGI development, driven by human researchers, fundamentally cannot. Each improvement the ANDSI makes to its own architecture, training methodology, or reasoning process directly accelerates the next improvement, a recursive dynamic that AGI development, which still depends heavily on human insight and institutional pace, lacks. Even a modest early lead in capability, say, an ANDSI that is merely somewhat better at designing neural architectures than human researchers, could snowball into transformative gains within years or even months. The AGI path, by spreading effort across general competence, may paradoxically delay the arrival of superintelligence by diluting the very recursive leverage that makes the intelligence explosion hypothesis plausible in the first place. DeepSeek R1. The pursuit of artificial general intelligence (AGI), human-level reasoning across all domains, faces immense, unsolved challenges in areas like common sense, transfer learning, and causal understanding. In contrast, an artificial narrow-domain superintelligence (ANDSI) focused exclusively on the sub-problem of designing a full ASI could be developed far more quickly. By concentrating all its superhuman capabilities on a single, well-defined goal, such as optimizing AI architectures, learning algorithms, or recursive self-improvement strategies, this narrow superintelligence would not need to understand language, navigate physical spaces, or exhibit general wisdom. It would simply need to be vastly better than any human or current AI at the specific task of AI research, allowing it to short-circuit the decades of foundational work required to first build a general-purpose AGI. The AGI path is inherently slower because it demands solving a broad suite of cognitive competencies simultaneously, many of which are irrelevant to the ultimate goal of creating ASI. For example, an AGI would need to handle disparate tasks like planning a vacation, interpreting metaphors, and recognizing social cues, each a research sinkhole. An ANDSI for ASI design, by contrast, avoids these distractions. It can be built using specialized, narrow superintelligence techniques, e.g., massive-scale reinforcement learning on a closed loop of AI code generation, evaluation, and revision that are tractable with today's hardware and methods. This focused system could recursively improve its own design software, leading to explosive, domain-specific intelligence gains without ever achieving general understanding, much as AlphaZero became superhuman at Go and chess without developing general reasoning. Historical precedent supports this view. Narrow superintelligences have repeatedly surpassed human experts in constrained domains within years, while AGI has remained out of reach for decades. An ANDSI dedicated to ASI creation would leverage this pattern, using its narrow but extreme competence to automate the discovery of more efficient learning paradigms, novel neural architectures, or even hardware optimizations. Once this narrow designer achieves a working ASI which could then be generalized, the intermediate AGI step becomes unnecessary. Thus, by sidestepping the vast, unsolved problems of general intelligence, the ANDSI route offers a faster, more direct, and more engineering-feasible path to superintelligence. GLM-5. The case for reaching artificial superintelligence (ASI) more quickly through artificial narrow-domain superintelligence (ANDSI) rests on the efficiency of specialized optimization over the immense complexity of generality. Attempting to build artificial general intelligence (AGI) requires solving the broad compatibility problem, creating a system that can reason, sense, and act competently across every conceivable domain, akin to replicating the full spectrum of human cognition. This introduces massive computational overhead and architectural complexity. In contrast, an ANDSI focuses exclusively on the singular domain of computer science, chip design, and recursive self-improvement. By stripping away the need for social intelligence, motor control, or generalized world knowledge, engineers can channel all resources into creating a system that is superintelligent strictly in the task of writing better code, thereby reaching the threshold of recursive improvement much faster than a jack-of-all-trades AGI. Furthermore, an ANDSI specifically designed to achieve ASI offers a more direct trajectory for the intelligence explosion. While an AGI might eventually learn to code, it would first need to achieve human parity across various other modalities before it could effectively contribute to its own architecture. An ANDSI, however, starts at superhuman capability in the only domain that matters for growth, optimizing algorithms and hardware. This creates a tighter feedback loop where the system can immediately iterate on its own source code and design superior computing substrates. Because the fitness function of an ANDSI is ruthlessly targeted at intelligence amplification rather than general competence, it bypasses the plateau of human-level performance and immediately vaults into superintelligence, compressing the timeline for the singularity by removing the generalist middleman. Finally, the path through ANDSI is more tractable and less prone to alignment gridlock than the AGI path. AGI development is hampered by the unpredictability of emergent behaviors in large, general-purpose models, making safety assurances difficult and potentially slowing deployment due to regulatory caution. An ANDSI, by definition, has a confined output space and a specific objective function, making it easier to test, sandbox, and control during the critical ramp-up phase. Because the engineering challenge is constrained to a specific domain, the development cycle is closer to traditional software engineering than the exploratory chaos of cognitive science. This technical tractability means that an ANDSI could be built, deployed, and set to the task of solving the hard problem of superintelligence while AGI researchers are still struggling to synthesize common sense and general reasoning. Note about Grok 4. XAI must be strapped for cache because much more often than not recently it says that it can't generate a response due to high demand.